Hey everyone, I just want to make this video to show you how exponents work, basically. There's a few rules and they all come from the same place, just straight from the definition. And so I want to show you that. So let me pop up a whiteboard here and start going. So firstly, let's just get the basics out of the way, right? So an exponent is, here's a couple of terms. So if I have like 3x to the fifth, that didn't look like a 5 at all. 5, there we go. This thing out front is the coefficient. We are mostly not going to deal with those, but I do want to get that term out there, F-I-C-I-E-N-T, because I will use it a few times when we're doing some examples, and possibly more on the next topic as well. This right here is the base. That term we are going to use quite a bit. And then this one that I'm going to do in green, of course, that is the exponent. All right, so there's your basic terminology. Now, all an exponent is it tells you how many times to multiply something by itself. So like x to the third is x times x times x, and I'm guessing you already knew that. But that's really what an exponent is, just how many times you multiply. Now, I do want to make this point that I often see people not knowing, which is that an exponent or exponentiation, so the verb form of exponent is exponentiation, is to multiplication what multiplication is to addition, right? So if you have like 3x, that tells you I should add x to itself 3 times. Now we call that multiplying by 3, but really this is what it means, right? And then x to the third is x times x times x. So that's the relationship there. It's like the next step up in the addition to multiplication to exponentiation ladder. It really is a progression. Believe it or not, there is more after that you will almost certainly never hear of unless you go well up into math. It's called up arrow notation. It was invented by a guy named John Conway to, was it Conway? I think it was John Conway, to describe very, very, very large numbers. So it's there is something after this, but we're not doing it in this class. So anyway, that's what exponents are. They just tell you how many times to multiply by itself. Now, I'm kind of glossing that over a little bit, but this turns out to be where all the properties come from, right? We're going to have 6, 7, 8 properties, I think. And they're all, like, every single one of them, when I'm showing you why this property exists, I'm just going to go back to the definition and say, this number means multiply by itself that many times, right? You're going to hear me say that a whole bunch of times in this video. Yeah, and so just keep in mind what the definition is. It'll make a lot of things easier. It'll make it so that you actually don't have to memorize all the properties. If you just keep this in mind and are willing to kind of back up to that to remind yourself what the properties are, you'll have a really easy time with it. So here, let's do some properties. So properties. All right, this is going to take a little while because I'm going to do all the properties one at a time, give you an example of each one, and then explain why it's true. Probably in the other order. Probably explain why it's true, then give you an example. So if I have 2 bases that I am multiplying together, and they have to be the same base. So I have x to the a times x to the b. That is x to the a plus b. When I'm multiplying like bases, I add the exponents. The reason for that is this. Let's do this guy in red. Let's say I had x to the third times x to the second, right? So what that really means is x to the third is just x times x times x times x times x. And x to the second is x times x, right? That's literally just the definition. And so now I have 5 x's that I'm multiplying together, right? It's all multiplication, so x to the fifth. So that is the simplest of the properties. There's another one that's very similar, which is dividing. If I have x to the a over x to the b, that is x to the a minus b. Now I'm subtracting instead of adding, and the reason is canceling. So I kind of shot myself in the foot here with the room, but I'm gonna scoot over to the right. So let's say I have x to the fifth, let's say, over x to the third. Well, the top, x to the fifth, is 5 x's. X, and the bottom is 3 of them. Oop, I almost wrote 3 when I meant to write x. This is a fraction. You can cancel. Cancel. That's x to the second. So what this means is that we are taking away the ones on the bottom from the ones on the top. That's why it's subtraction. Pretty simple. All right, what if I have a power to another power? Not power to a power, but I have an exponential. I'm saying this badly. I have a base raised to a power. X to the second, let's say, to the third power. Sorry, I'm doing this out of order, my bad. If I have x to the a to the b, well, this is x to the a times b. Right now we're multiplying. The reason is, let's say I have x to the 2 to the 3. This is supposed to come out to be x to the 6th, so x squared is x times x. And that's to the third power. So that means I'm just going to have 3 of these 2x's, right? So this is going to be xx. I got 3 of those guys like that. And how many of them are there now? There are 6. So this is x to the 6th. Right? So this just says I have 3 copies of x squared, and those x squareds are each 2 x's. So now I have 6 x's. That's the property. All right, let's get into a little bit more with fractions here. So if I have a fraction to a power, so if I have like x over y to the b, we'll call it a, that is x to the a over y to the a. I can just sort of distribute. I hate using the word distribute here because it's not actually the distributive property, but I can sort of distribute the exponent that's outside the parentheses to everything inside. Reason for that? You'll never guess. It's the definition. So this is, so let's say I have 3/5 to the 4th power. That is 3/5 times 3/5 times 3/5 times 3/5. And now when you're multiplying fractions, of course, you just multiply straight across. So the numerator, I have 4 3s, that would be 3 to the 4th. In the denominator, I have 4 5s, so that would be 5 to the 4th. Exactly as advertised. All right, let me make sure. I think that's all the ones I want to hit. Yeah, I think that's all the ones I want to hit. Let me make a quick check here. Multiply, divide, fraction, or power to power, fractions. Yes. So those are the 4 basic ones that I really want to hit. And then there's 2 others that I want to do. But before I do that, I want to introduce, I want to do this, I want to show you this pattern. That's what I'm trying to say here. So I want to talk about what the 0 power means, right? So far we've just had very simple powers like 2, 3, 5, etc. But you can raise things to powers that aren't those things, right? You can raise them to zeros and to negatives and to fractions as well. I'm not going to talk about the fractions yet. I'm not going to talk so much about what they mean as much as I'm going to, no, I guess I will. No, I will. I was going to put that off until later in the course, but I think it would be maybe helpful now. But anyway, we'll get there. But I really want to talk about negatives and zeros. So negative exponents mean something specific, and 0 exponents mean something very specific. So before I do any of that, I want to show you this chart. So here's the idea. I'm going to use the number 2. This probably works better with variables, but variables make people uncomfortable sometimes. So I'm going to use the number 2 and raise it to a variety of powers. I'm going to start with 2 to the 1. 2 to the 1. That is 2. I think we can agree on that. Then I'm going to raise it to, I'm going to increase that power to 2 to the 2. 2 to the 2. That's 4. And 2 to the 3. That means I'm going to multiply it by another 2. So by the way, what I'm doing here is I'm thinking of it like this, where I'm adding another another number to the exponent here, which is the equivalent of multiplying by 2 again, right? Multiplying by another copy of 2. That's what increasing the exponent does. So 2 to the third is just 4 times 2, right? That guy's 8. And I'll do one more, and then we'll stop. 2 to the fourth is 16. Okay. You might notice that I've started this in the middle of the board, and there's a good reason for that. And I'll show you, I'm going to show it to you right now, but I want to get the pattern first. So when my exponents go up by 1, plus 1, right? When I do that, what happens is that this gets multiplied by 2 times 2, right, etc. Right? Every time I go up by 1 here, the exponent, that's supposed to be pointing at the exponent, and it's not. This exponent, you get a plus 1. And this, you get times 2 times 2. And you can see that pattern just continues forever because adding another 1 to the exponent means multiply by another 2, right? That's what exponents are. I want to think about this backwards. I want to think about not what happens when I increase the exponent by 1, but what happens when I decrease it by 1, right? So when I'm going the other direction, minus 1, what happens here? Well, you're dividing by 1 less 2, or effectively you can think of, or excuse me, you're multiplying by 1 less 2, so you can think of that as dividing by a 2. So when I go negative 1, when I'm decreasing the exponent, that makes this divide by 2 instead of multiply. Same thing again, of course. Minus 1, divide by 2. The reason I bring this up is that I want to continue this pattern going up. So what do you think is going to happen when I do the same thing again? I get 2 to the 0. Well, my pattern suggests that I subtracted 1 from the exponent, so that should mean that I divide by 2. And that's true. That's what I do. I divide by 2, and 2 divided by 2 is 1. Same thing again. What if I subtracted another 1? So now my exponents are negative. So if I subtract another 1 from the exponent, I'm going to have 2 to the negative 1. I'm kind of running out of room here. Ooh, I wonder if I can make this bigger. I can. Hang on one sec. This is so nice. When I mess this up in person, I can't fix it. Well, I can, but I have to erase everything. Ha! Oh my God, computers are great. Okay, so we're gonna keep going here. 2 to the minus 1. So again, of course, I'm going to stop drawing all the arrows. 2 to the minus 1 means that I should divide by 2 again. I have 1 less copy of 2, so I should divide by 2. Whoop, pencil. I should divide by 2 again. And 1 divided by 2 is a half. And again, let's do 2 to the minus 2. So if I take a half divided by 2, I don't know if it's obvious what that is, but a half divided by 2 is the same thing as a half times 1 over 2, right? Because this is 2 over 1, so I should flip it over and multiply just like with every other division. That's 1/4. And this brings up a good point. The way you want to think about a negative exponent is that it's telling you how many of the base you are dividing by instead of multiplying. That's really what negative exponents mean. And for me, the easiest way to think of that is another power in the denominator. Whenever I'm dividing, I'm thinking of multiplying by a fraction where the number is in the denominator. Not always, but that's a good way to think of it here. Right. So I'm going to get rid of this. I guess I never needed that in the first place. I just want some more space. So I want to make a point here. So let's jam that way down there. Okay, cool. So this 2 to the negative 2 is a 4th. And the way you really want to think of that is that it's 1 over 2 to the 2. because this negative is telling you how many 2's not are in the top, like up here, right? Like this is 1 over 1, and this is 2 over 1, and this is 4 over 1, right? And so every time you tack on another 2 by increasing the power, you're putting another 2 in the top of that fraction. Whenever you tack another negative on, you're putting a 2 in the bottom. So when I have 2 to the negative 3, that guy is 1 over 8, which is 1 over 2 to the third. And on up, right? That you can obviously make that number as negative as you want. And it just gives you more and more powers in the denominator. And that's what negative exponents are. They're just a way of saying we're not multiplying this many times, now we're dividing this many times, or we're multiplying by the reciprocal this many times is another way to think of it, right? So 2 to the negative 3 it's not a negative number, it just means that there's 3 2's in the denominator of your fraction instead of the numerator. That's literally all it is. This also tells you what 2 to the 0 is, right? It's just 1. But think about it this way as well. If this was a 3 or a 5 or an 18, if I did 18 to the 1, I would get 18. 18 to the 2 is 324, and 18 to the 3 is something. And then when I decrease the power, I'm taking this number, which is 18, and dividing by 18, and so I get 1 again. So regardless of what the base is here, this number is always going to be 1 because you're dividing the base by itself, and so you just end up with 1 every time. That brings me to my the two properties I wanted to mention, which are the 0 property. So if I have x to the 0, that's 1, regardless of x, almost. Except for x equals 0. Which is undefined. And the reason that's undefined is that 0 to any power, no matter how many times you multiply 0 by something, you always get 0, right? 0 to the first is 0, is 0. 0 to the second is 0 times 0, clearly 0. 0 to the third, 0, 0, 0, also still 0. So when you do 0 to the 0, it doesn't make sense for it to be 1, but everything else to the 0 is 1. So then math just kind of throws up its hands at that point. And we just say, like, we don't know. It's maybe one of them, maybe it's something else, but we're not going to define it. We're just going to say that 0 to the 0 is not defined. Yeah, I'll just leave it at that. I'm not going to do examples here. That's what the previous page was for. And then x to the minus a is 1 over x to the a. Right, and that's exactly what I was talking about here, where we had 2 to the minus 2 is 1 over 2 to the 2, 2 to the minus 3, 1 over 2 to the 3, etc. So those are your properties of exponents. Those are the things that we're going to use when we are simplifying expressions. Is there anything else I wanted to hit there? No, I don't think so. I think that's all I wanted to say. So I guess I will go ahead and leave it there. There was one video that I linked in the other resources by Math Antics, I think, who had a really nice splash screen with all the properties on it. So you can just go there if you want a nice little video review of all the properties. Yeah, and I'll go ahead and leave it at that, and I will see you guys in the next video.